record. Okay, so the last time we had an actual lecture was Friday. On Monday, we wrote the quiz, or you guys wrote the quiz, I should say, during the lecture period. My personal goal for turning around any quiz, like any marking, like a test or a quiz, is always a week. So you should have the results back by next Monday at the absolute latest. But hopefully I can get them done before that. But that's like the upper interval that I put on trying to get any of these things turned around. So Monday by the latest, but hopefully before, if I can get that done. I have to mark 2 quizzes, one for another class and then one for this class. So definitely before Monday anyways. Okay, so in terms of lecture material, or Monday at the latest. So in terms of lecture material, we finished off an ANOVA example, and then we started lecture set 5, but we started lecture set 5 by talking about residual analysis. So as a refresher, our one-way ANOVA is effectively what we use it for is to test whether or not there's evidence of a difference among a collection of 3 or more means. So we have a population, the illustrations we saw, we had populations of 4 means and populations with 5 means. And we wanted to, or rather we had 4 populations and 5 populations. And we wanted to know if there was an evidence of a difference among the mean of each of the 4 or the mean of each of the 5. The assumptions that we place on the one-way ANOVA procedure are that each sample that we're working with, so the sample from each population is an SRS. Each population is independent of the other, so there's no overlap or any kind of relationship between the populations we're working with. That we can assume that all populations are normally distributed, and we can assume that all populations have the same variance. To check for normality, the most common approach is to build an estimate of what is called, is to build an estimate of the error term that is attached to the one-way ANOVA model. So the one-way ANOVA model is given in equation 2 on slide 20 of lecture set 5. It's also given in lecture set 4. The error term, which is called epsilon, is this term here. And to check the normality assumption, we construct an estimate of this error term. That estimate is called a residual, and it is found by taking the observation of interest and subtracting its corresponding sample mean. So for example, in this in the illustration on slide 22, we have 3 different samples corresponding to 3 different populations. To find the residuals, we took the observation from the sample and subtracted its corresponding sample mean. Okay, so then in the 3rd column here, we have an estimate of error term. Okay. Then what we do is we take all of the error term estimates, so all of these residual values, and we construct a normal or a QQ plot of all of the values together at once, because every single one of these values should be normal with a constant variance and a mean of 0. So our residual plot for an ANOVA experiment consists of one plot, which considers all of the residuals at once, and we can use that to verify the normality assumption. Okay, and in SPSS, this is actually quite easy to do because, of course, the software does it for us directly. Now, to check the constant variance assumption, there are a number of different things that we can do. One approach is just to build a scatter plot of the residuals at each of their respective treatment means. So in this diagram here, we basically just have a scatter plot of the residual points versus its corresponding sample mean from the original data. And then we're just checking to see if the spread is the same between each of the different collections of points. Another approach would be to use the rule of 2. So we take the largest standard deviation divide by the smallest standard deviation. And if that is within a factor of 2, we would say that the variances are equal, though that's a somewhat crude approach. We could also construct a formal hypothesis test for variance equality, which is called the Levene's test. The Levene's test is essentially an ANOVA for variances. And in that situation, the null hypothesis is that the variances are equivalent versus the alternative that a difference exists. So when we use Levene's test, we're essentially looking to see if the p-value is greater than the significance level. And in that, what I mean is we're checking to see if there is, ideally we would find no evidence to reject the null if we took that approach. So there's a number of different ways that we can go about checking the assumption of constant variance. In a written situation, like on a test or an assignment, I would say the rule of 2 would be the fastest way, because you just take largest standard deviation, divide by smallest standard deviation. And as long as the value is within a factor of 2, then we can say the variances are equal. And I think that I think I defined the rule of 2 in lecture set 4, but I'll just write it down here so that you have it. So here's an example of rule of 2 for this illustration, right? So the rule of 2 is basically assume okay. So the rule is assume equal variance if 0.5 is less than S max. So this is S, little s subscript max divided by little s subscript min is less than 2. Okay, so here we would have 52.221 divided by 40.902 is equal to pretty clear that it's in within a factor of 2 though, because it would have to be over 80 to be outside of it, but five. So therefore assume equal variance since 1.277 is between 0.5 and 2. Okay. So that's the rule of 2. And as I said before, a very crude approximation to check for standard deviation. I mean, you might start to ask questions like why 2? Like why not 1.5 or 1.25? I don't know. This is what the rule of 2 states though. So this is not the best way to check because there are situations where the variances would fail a Levene test but would be within a factor of 2. But this would be like kind of the quickest way of getting around it if you're, on an assignment or something and building a residual plot and this kind of thing isn't reasonable because you're not working with any sort of software. All right, so that's a recap of the assumption part, which is actually the last part of lecture set 5. So now we're going to go back to the start of lecture set 5, and we're going to talk about what are called contrasts today. And by Friday, we should be up to the multiple comparison stuff, which is really the goal of this, of the next part of finishing lecture set 5, is to get up to a multiple comparison. Does anyone have any questions about the assumption part? I'm really paranoid about the recording thing now. Okay, I don't see any questions. So What is a contrast? A contrast is what we would consider a linear combination of the means. The symbol that we use to designate a population contrast is gamma. Effectively, what we are doing here is we are stating a general, or we are constructing a general way of comparing all of the different population means that we might observe in our illustration. So for example, if we think about the minke whale data, which we worked with in lecture set 4, this had 4 population means. The contrast provides us with a way of relating all of the population means to one another. The rules of the contrast are pretty straightforward. The coefficients that we place in front of each mean have to add to 0. And essentially what the contrast allows us to do is compare the treatment means in such a way that we could state there's a difference between mean 1 and the averages of mean 2, 3, and 4. Or there's a difference between the average of mean 1 and mean 2 and the average of mean 3 and mean 4. And the other thing the contrast allows us to do is directly compare 2 means. So actually, a 2-sample t-test, the null hypothesis for the 2-sample t-test, and what we're going to see in a little bit, multiple comparisons, they are really just special kinds of contrasts. So the contrast is kind of the general comparison or structure for comparing multiple population means in one hypothesis test. All right, so let's look at some illustrations of what contrast could look like. So let's use the minke whale data. So the minke whale data had 4 different population means associated with it, 1 mean for each depth. Okay? So we have mu1, mu2, mu3, mu4. Okay, this is, and each of these are average length of whale, and they're just at different depths. So this was depth 0 to 49, 50 to 99, 100 to 149, 150 to 199. Okay. So we have 4 population means. We want to build contrast about these population means, which basically just means I want to build hypothesis tests where I can consider all of the means at once. So we have only seen examples where we work with 1 population mean or we compare 2 population means. But what if I were on to run a formal hypothesis test about 3 population means or about 4 or 5 or 6? The contrast allows me to do this. The only thing I have to obey is that the means the means are linear, which means that there's no transformation applied to them, that the means are only added and subtracted from each other, and that the coefficients that I place in front of the means have to sum to 1. Okay, so that is the standard contrast. All right, so 1A, set up a population contrast that compares the average body length of minke whales entangled at depths of 0 to 99 to whales entangled at depths of 150 to 199. So what would this look like? Okay. So we have 4 population means. Right? We've already written out the depths that are associated with the mean. So this is literally the same table that I built on the previous slide, but I'm just bringing it over here so that we have it as a reference. So this is going to be 0 to 49, 50 to 99, 100 to 149, 150 to 199. I want to compare the average length of the whales between 0 and 99 to the length of the whales between 150 and 199. Okay, so the contrast is gamma equals C1 mu1 plus C2 mu2 plus C3 plus C3 mu3 plus C4 mu4. Okay, so in order for this to be a contrast, each mean can only be added and subtracted. All coefficients, which are these things here. Okay, so these are the coefficients. Okay. All coefficients must sum to 0. Okay, so basically when we set up a contrast, all we're really trying to do are pick the values of C of the coefficients, so in this case C1, C2, C3, C4, such that we can compare the means that we're interested in and such that all of the means sum or all the coefficients sum to 0. So there's a few different ways that you can go about doing this. One way that you can do this is as follows. So let C1 equal 1 over 2, C2 equal 1 over 2, C3 equals 0, C4 equals negative 1. Okay. So check if sum of C1 to C4 is 0. Okay, so I want to check this part here. So that's going to be 1 over 2 plus 1 over 2 plus 0 minus 1 equals 0. Check. Okay. Therefore, gamma equals 1 over 2 C1 plus 1 over 2 mu1 plus 1 over 2 mu2 plus 0 mu3 plus negative 1 mu4 equals mu1 plus mu2 over 2 minus mu4 is a contrast of interest. Right? So that's the basic idea when we want to set up a contrast. If we want to compare a collection of means to one another when we have more than 2 in the set, we just have to find a set of coefficients that allows us to make the comparison that we're interested in. And the only rule is that the means have to be added and subtracted to one another, and the coefficients must sum to 0. So the contrast that I presented here, gamma equals mu1 plus mu2 over 2 minus mu4, this is a valid contrast to compare the average length between 0 and 99 to the length between 150 and 199, because 1 over 2 plus 1 over 2 minus 1 equals 0. We could do this in a different way as well. So some students don't like working with fractions. Okay, so another possibility Another option would be C1 equals 1, C2 equals 1, C3 equals 0, C4 equals negative 2. That would work as well. So this gives us gamma equals mu1 plus mu2 minus 2 mu4. And we can see here that 1 plus 1 plus 0 minus 2 equals 0. Okay, so that's a perfectly viable option as well. it accomplishes the same thing. It's just written in a different way. Any questions?
Can we use decimals? Like, can we do C1.5, C2.5, and then C4 minus 1?
Yeah, that's the same thing as the half, so that's fine too. Yep. Any other questions? Okay, part B. So we'll look at another illustration here. Part B says, set up a population contrast that compares the average body length of minke whales entangled at depths 0 to 149 to the whales entangled at depths 150 to 199. Okay, so very similar idea, except basically what we're doing here is we want to compare the average of the first three means to the last mean. So again, there's a few ways that we could do this, right? So one option is we let C1 equal a third, which is 0.33 repeating. C2 equal a third, which is the same thing. And C3 equal a third, which is the same thing. And then we let C4 equal -1. So this would be one option. Okay, so we can check. So we have 1 over 3 plus 1 over 3 plus 1 over 3 minus 1 equals 0. So that's fine. So then the contrast would be gamma equals 1 over 3 mu1 plus 1 over 3 mu2 plus 1 over 3 mu3 minus mu4, which is mu1 plus mu2 plus mu3 over 3 minus mu4. Okay, so that's one way that we could do it. Another way we could do it is we could just skip past the decimal notation and we could go C1 equals C2 equals C3 equals +1, C4 equals -3. Okay, so this would give 1 plus 1 plus 1 minus 3, which is 0. So that would also work. Okay, and then this would give us a contrast of the form gamma equals mu1 plus mu2 plus mu3 minus 3 mu4. Okay, and that would accomplish the same goal. Any questions?
Sorry, just one more.
Yep.
In where you say like mu1 plus mu2 plus mu3 over 3 minus mu4, anytime there's no number in front, we just assume it's a 1. Would that be correct?
Yeah. So
Okay.
yeah, if you wanted to, you could just, there'd be a 1 there. Yeah.
Oh, okay, perfect. Thank you.
No worries.
I have a question.
Yes, sir.
So, contrasts are just allows us to tell like if there is a difference if like for example like mu1 is different from like mu2 or mu3.
Yeah, so we can use a contrast to compare mu1 to mu2, or we could use a contrast to compare mu1 to the average of mu2 and mu3.
Oh, okay. Thank you.
Yeah. So the contrast is like, so we've seen examples of we've seen 2 sample hypothesis tests so far where we compared mu1 to mu2 directly. So In two sample hypothesis tests, we had H0 mu1 equals mu2. This is the same thing as H0 mu1 minus mu2 equals 0. So that would mean that the contrast is C1 is 1, C2 is -1. Effectively, what the contrast is then is sort of the general way of structuring all different types of comparisons across a larger collection of means. So we've actually already done contrast. We just didn't tell you that that's what it was. And now what we're seeing is, because we're coming out of an ANOVA where we have 3 or more means, if we want to start making actual comparisons among the different means in the experiment, the contrast is our way of approaching that problem. And we're going to see one more result that falls out of this in a little bit, but I'll talk to it once we structure the test. So I went off the question quite a bit there, but to answer your question, yes, like it's just a way for us to compare a set of means within a larger pool of means. Okay, part C. So in part C, we have set up a population contrast that compares the average body length of minke whales entangled at depths of 0 to 99 to the whales entangled at 100 to 199. So basically what we're doing here is we're comparing the average of mu1 and mu2 to the average of mu3 and mu4. Okay, so we can do this in two ways. So one option would be C1 equals a half, which is 0.5. C2 equals a half, which is 0.5. C3 equals negative a half, which is negative 0.5. C4 equals negative a half, which is negative 0.5. Okay, and then we can check it. So we would have 1 over 2 plus 1 over 2 minus 1 over 2 minus 1 over 2 is 0. So that's fine. And then we would have our contrast, which is gamma equals 1 over 2 mu1 plus 1 over 2 mu2 minus 1 over 2 mu3 minus 1 over 2 mu4, which is mu1 plus mu2 over 2 minus mu3 plus mu4 over 2. Okay, so that would be one way that we can get at it. Another option would be C1 equals 1, C2 equals 1, C3 equals -1, C4 equals -1. So if we check this, we have 1 plus 1 minus 1 minus 1 is 0. So then the contrast is gamma equals mu1 plus mu2 minus mu3 minus mu4. Okay. Now, you might run into a situation where you have a more strict professor, and they might tell you that option 2 in each of these cases is not appropriate. The only reason, so from a hypothesis testing point of view, these two options will give you the exact same result. The only reason why option 1 is more appropriate is because it actually represents the question that's being asked. So the question says compare the average of mu1 and mu2 to the average of mu3 and mu4. Well, the average, by definition, is the sum of the means divided by the number of means. So the first option for each part, A, B, and C, that's the literal representation of the problem. But the second option for each part will get you the exact same answer. It's just not the literal representation of what the question is stating. But it's a workaround for students that don't like working with fractions, essentially. All right. Does anyone have any other questions about the setup? Students tend to hate contrast, so I don't want to rush this part. Okay. All right, so we've defined the contrast. What can we do with it? Well, basically, we can construct a hypothesis test about the contrast. And this is done by taking our contrast gamma and setting it equal to 0. So we can do all the usual things like, yeah, so C1, C2, C3, they are chosen based off of the question that is being asked. So for example, in part C here, part C says, set up a contrast that compares the average length of whales between 0 and 99 to the average length of whales between 100 and 199. So that's saying compare the average between mu1 and mu2 to the average between mu3 and mu4. So the values C1, C2, C3, C4, I have chosen based off of what I am being asked. The only rule is that the values of C1 to C4 in this case, they have to add to 0. So that's why there's two options. You can have kind of like a fraction option, which is literal representation, or you can have a whole value option, which will get you the same answer, but it just doesn't, it's not the literal explanation of what is being asked. Does that help?
I have a question regarding like 1A. So with that one, it's looking at mu1 and mu2 versus mu3, or versus mu4, but it doesn't mention mu3. So is that why it's 0 in your equation?
That's exactly why. Yeah.
Okay, thank you.
Yeah. And that's another reason why we can do 2 sample tests out of this, because let's say I said to you, compare mu2 and mu4. Well, then I can go C1, 0, C3, 0, and I just take them out, and I'm only left with mu2 and mu4. So you can get at 2 sample comparisons from the general contrast. But yeah, the values of C, we pick those ourselves just to represent the problem. Any other questions? Okay, so what do we do with a contrast? Well, we do the same thing that we did with everything else. We build a hypothesis test, right? Like that's every week we're going to do a new hypothesis test. Okay, so the hypothesis test in this case is a hypothesis test about the contrast. So basically we're taking the contrast that we built in the previous exercise and we're just setting it equal to 0. And that's going to be the null hypothesis in most cases. So the null hypothesis will basically be gamma equals 0 versus gamma not equal to 0. And that will allow us to test, for example, if the average of mu1 and mu2 is different from the average of mu3 and mu4. Now you can also do directional tests, but they're not as common. Usually we just look strictly for differences. So how do we test the contrast? Well, we collect our samples and then we build an estimate of gamma, which we call little c. So little c here is the estimate of gamma. So little c is to gamma what x bar is to mu. So little c is just a symbol. I don't know why we use c, probably because it's a contrast. Contrast starts with little c. Little c is basically just the sample contrast. So it is an estimate of gamma the same way that x bar is an estimate of mu, or the same way that s is an estimate of sigma. And just an estimate of the value that of the population value. Now, most often when we use contrasts, we are using the data that we had just run an ANOVA on. So that means that the assumptions of the ANOVA are the same assumptions for the contrast. So for the contrast, we will be assuming equal variance. When you assume equal variance, your true variance takes on a form that's shown here. Okay, so this is the variance of little c. And you can see that what that value is sigma squared population variance multiplied by the contrast coefficient squared over the sample size for all different coefficients in the population. To estimate sigma squared, I actually write that below. We use what is called a pooled variance estimate, SP squared. SP squared is equal to the mean squared error from the ANOVA. So again, our contrasts are going to follow the one-way ANOVA. So we compute the ANOVA first. Once we work out the ANOVA table, we have our MSE value in the ANOVA table, and we're just using that in the contrast. So our standard error of the contrast is just going to be the square root of the MSE divided by C1 squared over N1 all the way up to however many means we're comparing. Okay, what does this all mean in the context of a hypothesis test? Well, when we run a hypothesis test, we take the sample value, we subtract off a theoretical value. So for example, in a 2-sample hypothesis test, you go x bar 1 minus x bar 2 minus mu 1 minus mu 2, which is typically x bar 1 minus x bar 2 minus 0. And then you divide by an estimate of the standard error, which in the 2-sample case was the square root of S1 squared over N1 plus S2 squared over N2. Here, for the contrast, you can see that our test statistic is basically the same thing, except you have little c, which is the estimated value of the contrast, minus gamma, which is going to be 0 in most practical problems, divided by the standard error of c, which is the quantity shown at the end of slide 6. So when we want to run a hypothesis test about gamma, this is actually going to be just a t-test about gamma. So it's going to follow the exact same rules that our 2-sample test followed before. The only difference is what we are talking about now. So we're not talking about 2 means directly. We could be talking about any type of comparison within a pool of 3 or more means. Okay, so the assumptions for these tests are going to be exactly the same as the assumptions that we used for the one-way ANOVA. The confidence interval here will be built in the usual 3 steps. So you can see that on step 1, we find our t-value. Note that the t-value is on alpha over 2 and degrees of freedom error. So the degree of freedom for the t-value in a contrast is the degree of freedom error from the ANOVA table. And then you can see that the form of the contrast is just like it was before. So we have estimate, little c, plus or minus our t-value multiplied by standard error. So this is the exact same structure of any confidence interval we have considered up to this point in the course. We're just adjusting the formulas that are inside the interval because of what we are talking about. The hypothesis test is 6 steps. We can do directional tests about the contrast. Most often we'll just do difference testing, but you could do directional tests. So we would have 3 different types of hypotheses about a contrast. Step 2 is the usual. Step 3, test statistic. You can see here again, this is just contrast or estimated contrast value, little c, minus what's going to be 0 divided by the standard error of little c. Then we find a p-value or a critical value. Again, in each case, these are t's on alpha, comma, dfe, or t on alpha over 2, dfe, right? So anytime we run a contrast, our interval and our hypothesis test are going to agree as long as they use the same critical value. And then we just kind of just run through it like we usually do. Find the p-value, make a decision, write out a conclusion. It's all the same, just different formulas for a different situation. Okay. Illustrations. Okay, so for the minke whale data, in lecture set 4, we ran a one-way ANOVA. Here are the key outputs from that one-way ANOVA. So the mean squared error is 0.9. The F statistic is 13.742. And we have our 4 sample sizes, N1 to N4. Okay, part A. Suppose researchers wish to determine if there is evidence that the average body length of minke whales entangled at depths of 0 to 99 is different from that of whales entangled at 100 to 199 at the 5% significance level. Give the null and alternative for the test and estimate the standard deviation of the sample contrast. Okay, so what I'll do is I'll just kind of work through the test and then I'll highlight the answers along the way, but at least you can kind of see how the test would unfold if I kind of just sketch out the different parts of it. So in part A, we want to compare the depths at 0 to 99 to the depths at 100 to 199. So this is actually the third example that we started the lecture with. So gamma here is going to be mu1 plus mu2 over 2 minus mu3 plus mu4 over 2. So we have C1 equals C2 is a half, and we have C3 equals C4 is negative a half. Okay, so set up the null and alternative hypothesis for this test. So that would just be step 1 of our hypothesis testing procedure. So if we want to see if the average value for mu1 and mu2 is different from the average value of mu3 and mu4, then H naught is just going to be gamma equals 0 versus HA gamma not equal to 0. All right. Okay, now for clarity, let's take a closer look at what this is actually saying to us. So set gamma equal to 0. This gives mu1 plus mu2 over 2 minus mu3 plus mu4 over 2 equals 0. That gives mu1 plus mu2 over 2 equals mu3 plus mu4 over 2, right? So you can see that this is just a standard style of testing for a difference between two things. It's just that the two quantities that we're testing for a difference between are not individual means anymore, but they're an average of two means. But really, this is the same thing that we saw in lecture set 3 when we talked about independent two-sample t-tests. We're just upping the ante a little bit and using more than one mean on each side of the equality. All right, so then on step 2, we would have alpha 0.05. Now the question asks to estimate the standard deviation of the sample contrast. So why would we want to do that? Well, if we were to run the test all the way through, here we're going to have T is equal to C minus gamma divided by the standard error of C. Okay, so we need to get little c and we need to get the standard error. And the question is actually asking for this. So part B wants this. Okay. But let's just look at the whole thing so that we have an illustration of it. So first, gamma equals 0 because of the null hypothesis. That's the same idea as with a 2-sample t-test. It's the same idea as with a 1-sample t-test, except then we usually had different values. Little c is going to be c1 x bar 1 plus c2 x bar 2 plus c3 x bar 3 plus c4 x bar 4. Okay, so this is going to be 1 over 2 multiplied by x bar 1, which I need to pull up from lecture set 4. Okay, so on slide 8 of lecture set 4, we have those summary statistics. So 4.49, so we'd have 1 over 2 plus 4.49 plus 1 over 2 times 5.06 plus, minus 1 over 2 times 5.75 minus 1 over 2 times 5.99. All right, and then that gives us negative 2.19. So hopefully you can start to see what's happening here. Like we're just building a test statistic. Okay, and then we have the standard error of C. So that's going to be the square root of MSE multiplied by the square root of C1 squared over N1 plus C2 squared over N2 plus C3 squared over N3 plus C4 squared over N4. So that's going to be the square root of 0.990 multiplied by 1 over 2 squared divided by 39 plus 1 over 2 squared divided by 20 plus negative 1 over 2 squared divided by 28 plus negative 1 over 2 squared divided by 14. Okay, and that gives us 0.405928. And then we can see here t is equal to negative 2.19 minus 0 divided by 0.405928, which is negative 5.39950. And then from that point, everything is exactly the same, right? Like now you find a p-value, you find a critical value. The only difference is that the degrees of freedom is the DFE from the ANOVA, but everything works in the same way from this point forward. Okay, I'll stop there because I'm out of time. Does anyone have any questions about what has just occurred? Okay, so if there's no questions, as I said, I'll stop there for today. So we'll pick up from here on Friday. If you do have any questions, just let me know at any point via email or whatnot. And if I don't talk to you before then, I will talk to you on Friday afternoon at 1 p.m. Have a good couple of days.